Okay, let's get started. Welcome to lecture 6. So we're going to pick up today from where we left off last week. I know many of you probably just had a 61A midterm. So hopefully you're all relieved that that is now done. And, so I'm glad to really see everyone in lecture today. It's nice to have a lot of people here. We're going to be picking up basically today from where we left off. And last time we talked about pump systems, right? And we introduced this idea of matrices as linear transformations. So last time we had, whoops. Could we have both? Thank you. Matrix multiplication as linear transformation, right? So we started talking about that last time, and we're going to build from this. And one of the things that you might have known about functions in mathematics that you've encountered before, let's say you have a function that takes whatever number you give it and doubles the number, right? How do you recover the original number if all you get is the output of this function? You divide it by 2, right? If your function is doubling your number, then what do? You divide it by 2. And so if I have, let's say, some f of x, which gives me 2x, and then I have some g of x, which is equal to 1/2 x, what do we say about these functions? These are inverses of each other, right? These functions are called inverses. And today we're going to talk about inverses, but in the context of matrices and linear transformations. So we're not going to be talking just about inverses of functions on scalars or numbers like this, but we're going to be talking about inverses of functions that are operating now on vectors, because we're talking about matrix multiplication. In the physical world, you often don't encounter true inverses, right? Like, for example, if you eat your neighbor's sandwich, that function is not invertible. You can't give back the sandwich. You ate it already. But thankfully, in mathematics, we actually do have invertible functions, right? So if you make a mistake, you can actually revert back to your previous setting. And that's what we're going to be talking about in today's lecture and building on it in Thursday's lecture. So before we go into all of these details, few administrative announcements. One was we were told that the webcasts might be a little bit hard to see. And so we are working on a solution. The amazing people up there are helping us out. And so please say thank you to them if you ever see them. And they're going to try to have a bigger version of the document camera visible on the webcast. So hopefully this helps everyone. There's going to be some trade-offs involved, but we'll try and iterate till we get a solution that works. So that's the first announcement. The second announcement is that homeworks, as you might have noticed, are starting to pick up. And I want to emphasize that in this class, homeworks are the best preparation you can do for the exam. So the midterm will be heavily based on the homework problems that you see. And so I highly recommend doing your best to do the homework. We will be trying to release practice problems with every homework set, so that in addition to the homework, you have some extra problems that you can work on for extra practice. This will help you with getting ready for the exams. If you have questions, again, please come to office hours, please come to discussion. It's really, really effective for us to be able to talk to you one-on-one and it's more fun for us, and hopefully it's more fun for you. So I encourage you to come in. Okay, so with that, technical announcements are out of the way, and let us get started with our material. Today, the bulk of our lecture is going to be about matrix inversion. And the kind of surprising thing that I want hopefully everyone to realize is that there's actually nothing new that we're going to learn in today's lecture. Today's lecture is almost entirely talking about everything we've talked about in the previous weeks, but just putting new labels on things with minor tweaks here and there. So conceptually, I want you to think back every time I say something in lecture today, where have I seen this before? Right? Is this related to something I already understand? It won't be exactly the same, but it'll be very related. So we're going to do matrix inversion. Since you folks have been asking for more proofs practice, we're going to do another proof, a proof about inversion. And if we have time, we'll start talking about null spaces. But if not, we will just push that to next week. So let's start. Let's say now I give you the following transition matrix, right? We've done, last time we drew a bunch of pump diagrams, and then we do the transition matrix. Let's try and go the other way around. So I give you a Q, which is the following: 1, 0, 0, 0, 1, 0, 0, 0, 1. And I say x of t plus 1 is equal to q times x of t. Why don't you take a minute and draw the state transition diagram for this? You know, let's say you have 3 reservoirs, A, B, and C. The arrows are representing pumps. You know, just do this out yourself. This is big enough for people to see in the back, right? Yeah. Question? Even bigger? Okay. Well, I might not be able to fit the page, but let's see. Is that better? Okay, so how many people have the diagram for this? Yeah? Do people verify with their neighbor that they drew the same picture? Yeah? So how did you draw it? Let's say we have A, B, and C. What do we know about the water in A? It's going back to A, right? So all of the water is going back to A. What about B? All going back to B, all going back to C, right? This is a particularly boring pump, possibly the most boring pump that you could make, right? Because what is changing in this system? Nothing, right? So if you wanted to find the inverse of this operation, if you wanted to say, well, I operated my pumps, and now I have 1 liter of water in A. What was in A in the previous time step? 1 liter, right? Exactly. Because, well, nothing is changing. So here's a particularly simple example. And this is actually a transformation that we've seen before. It's called the identity transformation, right? Or the identity matrix. Because it basically keeps x of t exactly the same. So if this operation keeps going many, many times, then great. You know, that's not particularly interesting. But we can have multiple different pumps operating, and we want to understand complex interactions of pumps, right? So before we get to, you know, having a discussion about inversion, let's consider a different, slightly different setup. Okay, let's see how I can do this. So let's now consider Q equal to 1, 0, 0, 0, 0, 1, 0, 1, 0, and R is equal to 1/2, 0, 0, 0, 1/2, 0, and 0, 0, 1. And let's say I tell you that x at time 1 is the following: 1, 2, 3. So I have some amount of water in A, some amount of water in B, and some amount of water in C. Oops, you cannot see this. Okay, don't here. A, B, C. And you have 1 unit of water inside here, 1 unit in the next one, and 1 unit in the third one. One unit inside. This has 2, or this has 3, and this has 2. And I don't want you to draw the transition diagram for this particular pump. But I tell you that I run Q once, and then I run R once, right? What do I get after I run both of these pumps? So I basically have x at time 2. If I run Q on x of 1. And then I have x at time 3, which is I run R on x of 2. This is what I do. So can you go ahead and calculate what is the water at time 2 in each of the reservoirs? You know, don't even worry about drawing the diagram. We did this last time in class, right? We did a very similar example, and we said, well, what is the matrix doing? The matrix is representing the linear transformation. So this is representing the amount of water. This vector is representing the amount of water in each reservoir. And Q times X, this matrix vector multiplication, actually then tells us what happens at the next time step, right? So what multiplication do you need to do to be able to figure out what x of 2 is? Volume. Q times x, right? So how many people need a minute to do that multiplication out? How many people are done with it? Okay, so can someone tell me what x of 2 is? 1, 2, right? What happened? Basically, the water from B and C switched, right? Does everyone see that? Okay, and now what happens when you run R on top of that? What is x of 3? One half, 3 halves, 2, right? So now I've run these 2 pumps sequentially, and I've gotten, you know, the state vector that happens after running it twice. If instead of running the 2 pumps, one after the other, I wanted to just run 1 pump and still get to this state, what pump should I design? I should design basically the matrix multiplication of these, right? And remember, the order is important. So I have x of 3 is R times x of 2, and I can write this as R times Q times x of 1, right? X of 2, I'm substituting using this equation. Does everyone see what I'm doing here? So it's important because I see often a lot of students who sometimes get like tripped up between, is it Q times R or R times Q? Which is acting first, right? The first pump that acts is the one that is closest to the vector. Then the second one acts afterwards. Is everyone clear on that? Okay, so if I wanted to just run these once, I just wanted to run one pump, I can also just equivalently run RQ as a pump. Okay, so now we understand how pumps run sequentially, we understand the identity pump, so we're basically set. So now, what if I have another transition matrix? 2, 0, 0, 0, 2, 0, 0, 0, 2. And this is a really simple one, A, B, C, so let's try and now figure out our first kind of non-trivial inverse here. So there's something interesting about this pump, right? Let's say the reservoirs represented not tanks of water, but they represented reservoirs of energy. Who wants to buy this pump? Right? This is what is basically a non-conservative pump, right? You keep running this pump, and you just keep doubling the amount of water or amount of energy in your reservoir. This is exactly what we need, but we don't have this. So just as a side note, we will call if a pump is generating water, energy, etc. That's one case. What's another case? Let's say you had, instead of 2's here, you had a half or a third. You're basically losing, right? Every time you run the pump, your energy or your water is leaking away. Both these kinds of pumps, if a pump leaks, these are called non-conservative pumps. So the pumps we looked at last time, you'll notice, is that they are conservative pumps. And you'll see this actually showing up in your homework. For those of you who have looked at the pumps question on the homework, you know, this is something that you're going to have to start thinking about. And basically the question is, does the pump generate water energy? Does it leak water energy? Or does it, you know, just all stay somehow within the system? But now that we have that terminology out of the way, I have here that x at time t plus 1 is equal to q times x of t. And I now, again, want to recover x of t from x of t plus 1. And what I want to do for this is I don't want to just guess it. I want to design the pump that I can run. I want to design the pump such that I can press that button and have my tanks revert to the state that they were previously in. So what would that pump look like? What would that be? Does anyone have any ideas? Yeah? Yeah. I don't know what Q inverse is. 1/2. What one? Where 1/2? Okay, so you're saying let's choose an R equal to 1/2, 0, 0, 0, 1/2, 0, 0, 0, 1/2. And how would I draw this? I would draw this leaky pump, right? A, B, C, and each of them would have these leaky nodes on them. And let's just verify that this is actually correct. So you have x of t plus 1 is equal to q times x of t. And I have x of t is equal to, I claim, r times x of t plus 1. So now, if this is true, I better have q. I'm going to take this and substitute. And then I have basically r times x of t plus 1. Yeah, question? Well, order in general will matter. We will come back to that question. But here, we're just doing a substitution, right? There's nothing about the order of the pumps even coming up. So all I want to focus on for here, I don't want to think particularly about the order. We will come back to the order question in just a couple of minutes. But now, what do we have? We have basically q times r times x of t plus 1. And if q times r is a joint pump that gives me back the original state, if I keep running qr, 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 what is the pump that this is actually representing? The identity pump, right? And so what we have is q times r equal to identity. And here, if you check this by multiplying these out, you'll see that that is exactly indeed true. The question, of course, is, how do you do this for much more complicated systems? And that's what we want to try to get at in the rest of this lecture. So I want to define for you now the definition of an inverse. We've done a couple of inverses. Matrix P is said to be the inverse of matrix Q. Both are square matrices if P times Q is equal to Q times P equal to identity. So what are we saying here? We're saying we want, if you operate P first and then you operate Q, you will get an identity. If you operate Q first and then you operate P, you will still get an identity. So the question that was asked right here on the right about the order, this is being addressed exactly in this definition. And we'll actually come back in a few, at the end of the lecture, to show why there's not even any issues with having this kind of definition. Sometimes we will denote P as Q to the power minus 1. And this is read as Q inverse. And this is just borrowing from notation that you've seen already in algebra, right? Any questions so far? Okay. Since everything's good, let's do an example. So now, let's say I have the following pump system: 0, 1, 0, 1 half, 0, 1, 1 half, 0, 0. Why don't you take a minute to draw out actually the pumps, what the pumps look like for this Q? Yeah, question. Great question. Are only square matrices invertible? For now, yes. In general, invertibility, also the answer is yes. We're only defining invertibility for square matrices. Towards the end of this class, and more in 16b, you will see how to define a notion of what we call a pseudo-inverse for a non-square matrix. So it's kind of like inversion, but it's actually not the same operation at all. So there are some transformations that will have an inverse, and other transformations will not have an inverse at all. And we will actually see that there are even some square matrices that will not be invertible. Good question. So what does the diagram for this look like if I have A, B, and C? Anyone want to tell me how the arrows are going? A's water is flowing out, and where is A's water coming in from? Right? When you're in doubt about how to write a transition, like how to draw the transition diagram or how to draw, the matrix, just go step by step and write out all of the equations. I'm not going to do it right now in the interest of time, but please, I recommend that you do it. So here we have basically A is spilling out half into B, half into C, and then we have B is going to A, and we have all of C is going into B. And we want to now find, we have x of t plus 1 is equal to q times x of t. Want to find p such that, or x of t is equal to p times x of t plus 1, right? We want to find this in per our definition up here. And what do we know about this? We know that we have x of t is equal to p times x of t plus 1. So we have, actually let me not write it this way. Let me write it. X of t plus 1 is equal to q times x of t, which is equal to q times p times x of t plus 1. Which implies that I want q times p to exactly be equal to the identity. So now I've already told you that we're basically doing nothing new in this lecture. Right? This lecture is basically entirely review in some sense. So if I want to now have q times p equal to identity, I want to be able to figure out what p is, right? Have I seen something like this before? What have we been doing so far for the past couple of weeks? There's like one type of problem we've been solving, right? Systems of linear equations using Gaussian elimination. And there we've been saying, let's look at things like ax equal to b. Whoops, yeah, sorry, wrong paper. Here. But here, x and b are vectors. Right? B is known, x is unknown. In this setup, is q known to us? Yes. Is identity known to us? Yes. What is unknown? P. So it's exactly the same pattern, except instead of the vectors, what do we have? Matrices instead of vectors, right? But remember, now, matrices are just stacks of column vectors, right? You just take a vector, and then you put another vector, and you put another vector, and you put another vector, and you get a matrix. So it turns out that we're going to use the exact same tools that we use to solve systems of linear equations to actually figure out how to invert a matrix. So let us write this out. I have Q, which is 0, 1 half, 1 half, 1, 0, 0, 0, 1, 0. And now let's write out P explicitly. What are the entries of P? I have P1, 1, P1, 2, P1, 3, P2, 1, P2, 2, P2, 3, P3, 1, P3, 2, P3, 3 is equal to 1, 0, 0, 0, 1, 0, 0, 0, 1. And I have these basically stacks of column vectors. So now, what do you feel like doing? Right? If we call these vectors, let's say this vector is P1, this vector is P2, this vector is P3. I know, basically, that Q times P1 is equal to 1, 0, 0, right? I can basically transform this back into the exact same type of thing that I knew how to do. Except now, do I really want to do 3 Gaussian eliminations? I hope the answer you say is no, because I don't want to do 3 Gaussian eliminations. But what can we do when we do Gaussian elimination? Do the entries in the B vector on the right-hand side matter? No, the steps only depend on the entries of A, right? So what can we do? How can we actually solve this stuff? Can we set this up as an augmented matrix problem? So I'm going to make the augmented matrix. And how many columns is my augmented matrix going to have? 6. So first 3 columns are going to be the columns of Q. Then I'm going to draw my line, and then I'm going to write 1, 0, 0, 0, 1, 0, 0, 0, 1. So now, what do you feel like doing? Gaussian elimination. So go ahead. Why don't you do this Gaussian elimination? And let's converge back in a minute. If you need a stretch break or just want to, doodle for a minute, do that. But make sure you also know how to do this Gaussian elimination. Are there questions on why we have 3 columns here? Yeah? What? Excellent question, right? Why do we have 3 columns here? So the first column represents the equation Q times P1 equal to the first column of the identity. So when I do matrix-matrix multiplication, remember I can do matrix-matrix multiplication as a stack of matrix vector multiplications. So I do this matrix times this vector and I write it. Then I do this matrix times this vector and I write it here, right? So on and so forth. So I'm just kind of copy-pasting that. So then I have Q times P2 is equal to 0, 1, 0. And I can write Q times P3 is equal to 0, 0, 1. And so I could just do this Gaussian elimination, right? And I would get some solution. But then I would have to write a second Gaussian elimination for this guy. Does everyone see that? But because the stuff here, the row operations are only going to operate on Q, I can just stack all of these together. This is not the simplest thing. Like, it's really good to ask questions about this. Other questions? Yeah. How do we know that this is a legal mathematical process, the stacking of the columns? Good question. Why do we know we're not breaking anything here, right? We know that we have these three equations, right? And we know that we can solve this one, and this one on their own terms. But the key observation that we are using is that Gaussian elimination steps do not depend on the B vector. Gaussian elimination steps for AX equal to B. And so literally, one thing that is, like, if you're uneasy with this, one thing that it's worth doing is just do the Gaussian elimination, assuming that you had just this as your augmented matrix. Right? This seems perfectly legal, right? Writing just this column is also perfectly legal. So do it like this, and you'll see that you'll get a certain configuration here. You'll see that even no matter what column you put here, the configuration here will be exactly the same. In fact, when you do Gaussian elimination, what is your terminal point? Right? In most cases, what you get here is an identity matrix. It doesn't depend at all on this, right? So the order in which you perform your row operations, we don't care. Good question. Other questions? Question? What is the geometrical meaning of having a 3 by 3 answer vector? So here we actually have 9 unknowns, right? So we have an entire matrix. So you can interpret it as a vector just by stacking it, but we really want to actually keep the matrix structure for it. So you can represent, if you have a system of equations, you can reorganize them in any way. Okay, so what are the steps that you took to do this Gaussian elimination? First step, you swap the rows, right? So you swapped R2 and R1. So why didn't someone just call out numbers and I can write them? 0, thank you. Half, 0, 0. And then what do I have here? 0, 1, 0, 0, 0, 0, 1. Great. Then what do I do? I can normalize the first row, right? So I basically multiply the first row by 2, which gives me 1, 0, 2, 0, 2, 0, 0, 1, 0, 1, 0, 0, 1 half 0, 0, 0, 0, 1. Then what do? I basically use the first row to cancel out the third row, right? So I have 1, 0, 2, 0, 2, 0, 0, 1, 0, 1, 0, 0. And then here I have 0, 0, negative 1, 0, negative 1, and 1. Right? Is someone checking my algebra? Okay, good. Now I multiply R3. Now I have a negative 1. I don't like negative ones. I do R3 times minus 1. 1, 0, 2, 0, 2, 0, 0, 1, 0, 0, 0, minus 1, 1, 0, 0, 0, 1, negative 1. And this becomes a plus 1. Right? Okay. Now what remains to be done? What form am I in? I'm now in a reduced echelon form, right? It's upper triangular. There's a triangle here. Everything below the triangle is zeros. I have this nice triangle. Great. Now I just want to cancel this person out, right? So now I do 1, 0, 0, 0, 1, 0, 0, 0, 1, and I have 0, 0, 2. I get 1, 0, 0, 0, 1, negative 1. Does everyone get the same answer? Okay, great. So, what are these? What is the first column here representing? P1, right? So this is P1. This is P2. And this is P3. The question was, didn't we swap rows? Yes, we did. Great question. Didn't we swap rows? Doesn't that change these things? What does swapping rows mean? Swapping rows means swapping the order of the equations. It's not swapping the order of the variables. Right? This is a good, very, very good question. I'm so glad you asked it. Like, it's important to remember that swapping the rows does not change which variable is where. Yeah? The question is it still Gaussian elimination if you use a different set of steps to get to row echelon form? There's different answers to that. One is that the exact steps that we follow, like there's a normalization, that you do. This is the process of Gaussian elimination. However, there's many different ways of arriving at the correct answer. And the whole family of algorithms, to some extent, is called Gaussian elimination. The precise algorithm that we're defining in this class has a certain order in which you do the operations. Yeah?
So adding on to that, like let's say instead of swapping row 1 and row 2, like you swap row 1 and row 3, would that technically still be Gaussian elimination?
Great question. If instead of swapping row 1 and row 2, you swap row 2 and row 1 and row 3, would that still be Gaussian elimination? The answer is yes. At the back there, I saw a hand. Other questions? Yeah.
So normally, if we have like an augmented matrix where the right side is a vertical line, let's say there's just like one vector, right, and it's in like reduced row echelon form, we say like, oh, x is equal to like the top one, y is equal to the middle, z is equal to the bottom.
Yeah.
So like, what does that mean? Like,
excellent question. So here the question is, when you have something like this, the question is saying, well, I can use the elements of B. Oops, thank you. If I have something like this, and I do row reduction, I do Gaussian elimination, whatever I get on the right-hand side, I can match to each of my variables. So let's do that here. We said that the first column corresponds to P1. What is P1 here? This is P11, this is P21, and this is P31. This is P12, this is P22, this is P32. And this is P13, this is P23, and this is P33. Does that answer the question? Yes?
Can you explain again how you got the initial matrix?
The initial matrix, the Q?
The side by side.
The what?
The six column one.
Okay, So here what I did was I just said, I have this equation, right? Q times P equal to identity. And I'm just writing that as Q times P1, Q times P2, and Q times P3, where P1, P2, P3 are the 3 columns of P. And then here, instead of just writing out these 3 equations one at a time, I'm writing them out all out at the same time. So instead of just having 1 column here, I have 3. OK. So now we've done this. Of course, the question is, let's go back to our definition and make sure that our definition is actually something that we're really allowed to say. There was this question about order. So here I'm going to prove a theorem. And I'm going to say, if Q times P equal to identity, and R times Q is also equal to identity, then we must have that R is equal to P. Some might refer to this theorem as saying that the left inverse and the right inverse are the same. Why is it important to have a theorem like this? We know when we're multiplying scalars, when we're just multiplying numbers, it doesn't matter which order you do multiplication in, right? But we know for matrices that the order of multiplication does matter, right? It does not commute. It just so turns out that in the case of inverses, it doesn't matter what order you do the operations in. So if I give you if I say P is, if you multiply Q on the right-hand side by P, which is what is called the right inverse of Q, or if you multiply Q on the left-hand side by some R, which is what is called the left inverse, they must be the same. So, why don't you try to take a minute to think about how you would prove this? Feel free to talk to your neighbor, just scratch your brains a little bit, get warmed up to the idea. Remember the steps, right? First, write down what you know, write down where you want to go, then manipulate. How many people would like another minute to think about this? How many people are ready to move on? Okay, another minute. When you're stuck on a proof, I encourage you to write stuff out. You might even just scribble or doodle or draw a picture, but keep generating stuff on the paper. Okay, let's try to do it together. So, let's write out what we know at the beginning. We say, well, I know Q times P equal to identity, and I know R times Q equal to identity, right? Where do I want to go? I want to have R is equal to P. Right? I haven't proved it yet, but I'm just writing it down for my reference. Okay, so if I want to kind of have R is equal to P, then I want to have one side of the equation with R on it and the other side of the equation with P on it, right? And one natural thing to try is to say, hey, look, these are both equal to identity. Let's try to put them to equal to each other, right? But you have Q on both sides, and ideally you would like to be able to cancel that Q, but you can't, right? Doesn't work, right? You can say that Q times P is equal to R times Q, but you can't cancel Q because it's on different sides, and you can't use that as a step. So what can we do? We can say well, I have, let's say, Q times P equal to identity, and I want to somehow get R involved, right? What is the nice thing about identity? I can multiply it by something and get the thing back, right? So I'm going to say, okay, let me multiply both sides of this equation by R. So I'm going to say R times Q and R times identity. What does this imply? I have R times Q times P is equal to R. But now, what do I know about R times Q? It's the identity, right? So I have the identity times P is equal to R, which implies that P is equal to R. So this step, which you would hope would work, doesn't work. And here, there's something to observe, right? Something I want to point out here. I could have chosen to do the following. What we did not do. We could have said Q times P is equal to identity. And after we had written this out, what we could have said is, I want to get R, right? We all agreed on getting R. And I chose to multiply by R on this side. We could have chosen to put an R on this side, on the right. I would have still gotten the R I wanted. But on the left, I would have had Q times P times R. Right? And then I can't do this, like, I don't have this nice pattern that emerged. So I chose to multiply on the left because I saw that I knew something about R times Q. Whereas here, I don't know anything about P times R. Right? That's why I made that choice. Yeah, back. Good question. You can say Q times P equal to identity, but then you get R equals R. Right? Like, that's exactly the natural thing to do. So you have this. This is identity times R equal to R, but it doesn't help us in the direction we need. Yeah, question in the back?
Multiplying both sides
So the question is, why didn't we multiply by both equations on the right by Q inverse? Well, first, we don't necessarily know that Q inverse exists. This is part of the existence proof. Secondly, here, you would have to multiply one side on the right and one side on the left by Q inverse, which you can't do. Other questions? Yeah? Because that's not given to us in the theorem statement. Right, so we want to try and justify the definition, right? We cannot use this to justify the definition if we assume that Q inverse exists. Yeah? There is no notion of matrix division. Matrix inversion is kind of the closest that you will get to matrix inversion. So we can't do that. Yeah. So I want to emphasize that, like, you know, there's an element of systematically writing stuff down and trying stuff out, and like writing out all of these like things that are gonna go wrong in the path to getting the right proof. Like, if you're stuck, try stuff out, like massage things around, keep doodling. Okay, so we have this, and I want to move to the second proof that we're going to do, but we're going to come to it. And you folks have already been asking all of the right questions to move to this last part of what I want to talk about. And we talked about the sandwich example at the beginning of the class, right? So we first talked about, you know, f of x equal to 2x. And we said that g of x equal to 1/2 x was its inverse. What if f of x is equal to 0x? You give me a number, I multiply it by 0 and give it back to you. Can you recover your number? No, right? Does an inverse exist for f? Doesn't exist, right? So do you expect that inverses will always exist for all matrices? Nope. So what if we think of the following system of transformation? So I have reservoir A, reservoir B, and all of the water from B goes to A, and A also keeps all of its water. So what is the transition matrix for this? Basically, A is getting the water from itself and from B. B is getting the water from nobody. And I tell you that, hey, I ran this pump, and I found 2 liters of water in A and 0 liters of water in B. What was the situation in the previous time step? Can you recover it? You're stuck, right? Because, well, it could have been that A was empty and there were 2 liters in B and they all flowed over to A. Or it could have been that B was originally empty, or they each could have had a liter. You have no idea, right? So here, you cannot recover x of t from x of t plus 1. Inverses need not always exist. So we see that inverses don't always have to exist from this intuitive example, right? And we've also seen now that Gaussian elimination is very connected to inversion, right? Finding the inverse is like doing Gaussian elimination. And this whole time we've been talking about, well, you know, is Gaussian elimination going to give us a unique solution or not? Right? But turns out sometimes Gaussian elimination doesn't give us what we want, right? It doesn't give us a unique solution. Sometimes we get these rows of zeros equal to 0, or a row of zeros equal to a 1. Not a good situation. And we saw that a way to understand the connection between Gaussian elimination and matrices was through linear dependence and independence, right? So now what we're going to do is we're going to take that one step further, and we're going to make a connection. So we know that inversion is connected to Gaussian elimination. And we know that Gaussian elimination and unique solutions are connected to linear dependence and independence. And now what we're going to try and do is tie all of these things together. The full understanding of how all of these things are connected, we will only be able to show you by the end of 16B. There's a couple of things that will still be, a little bit of holes. But we're going to take one major step into connecting all of these things up. So here, do you want me to write on this paper or a new paper? This paper? Okay. No, is there new paper? Hands up. This paper? Okay. Theorem. If the columns of A are linearly dependent, then matrix A is not invertible. When you look at this Q here, what do you notice about its columns? They're the same, right? Are they therefore linearly dependent? Absolutely. Turns out this is not just the one contrived example that I came up with. You will find this for every, if you have basically a matrix where the columns are linearly dependent, every such matrix will not be invertible. It's not just this one that I constructed. Okay, so this statement is again of this form where I have something, some statement P implies some other statement Q, right? I want to write this in a different way just because I think you might encounter it sometimes, and I want to introduce you to this way of writing things. So another way to say the same thing. So here I'm saying P implies Q. So for example, if it is raining, then there must be clouds. Right? P is it's raining. Q is there are clouds. Okay? So now if I know that this is always true, and so this is raining, rain, clouds. What if I told you that there were no clouds in the sky? What can you infer? That it's not raining, right? Because you're going to say that if there are no clouds, well, if possible, let it be raining. If it was raining, then there would be clouds. But, oh, I know that there are no clouds. Hence, my initial assumption of it being raining must have been incorrect. Right? Do you see how that argument proceeded? So when we say P implies Q, this is equivalent to writing not P, or not Q, implies not P. And I will tell you a piece of jargon, despite my dislike for it, just so that you will know this. This is sometimes called a contrapositive. We will not be expecting you to, know this or have these kinds of, these terminology we don't care about whether you know it or not. Not in this class. In CS70, you'll talk in much more detail about this. But that's why this is the class that comes first, and you take CS70 later. We're not going to go into any of the details of this here. But now, in the context of the problem that we're talking about, right? What is another way to state this theorem? We're not proving it, but we can say that if matrix A is invertible, which means that A inverse exists, right? I'm saying not Q, so here matrix A is not invertible, so the opposite of that is matrix A is invertible. This implies the columns of A are linearly independent. Okay? So I just want to point out that these two statements are two ways of saying the same theorem. They're not different theorems. If you prove one of them, the other one is naturally true. So now let's prove them. Okay, so proof. So we have basically, if the columns A are linearly dependent, so we know, let's say we have that the columns of matrix A are linearly dependent, right? So we know that, let's say, C1A1 plus C2A2 plus Cn an. I'm going to use the second definition of linear dependence is equal to 0, where all Ci's are not 0. I know that the columns are linearly dependent. Where do I want to end up at? I want to end up by saying that A inverse does not exist. Right? So when you want to prove something does not exist, that's kind of a hard thing to prove, right? Like, if you want to prove something exists, then you can, like, build it. If you want to prove a unicorn exists, you can, like, bring a unicorn, right? That's a great way of proving a unicorn exists. But how do you prove it doesn't exist? You can say, I looked a lot and couldn't find one. But that's not a proof, right? So when you want to prove something doesn't exist, a good strategy is often to say, well, maybe it does exist. Let's pretend, right? This is a suggestion that sometimes you might want to try a proof by contradiction. So we'll say, maybe, if possible, let A inverse exist. Okay? We're going to say, if possible, this is true. Let it be true. So now let's take what we know. And again, we have these columns, but we know something about the matrix A, right? So we want to write this now in terms of the matrix A. So I'm going to write this instead A times C1, C2, Cn equal to 0. This is basically the same expression written, right? And I know now this vector C is not the 0 vector, right? Why do I know that the vector C is not the 0 vector? By my definition, essentially, right? By my assumption, by this linear dependence. Okay. Now I know that A inverse exists. And I have an A here. I'm pretending A inverse exists. What is it very tempting to want to try and do? Multiply both sides by an A inverse, right? You want the A and A inverse to like come together. So I say, let's take A inverse times A times my vector C, which is equal to A inverse times 0. Multiply by A inverse. Now what do you want to do? Someone at the back. Use the associative property, right? So now I have A inverse times A. What is that? Times C is equal to A inverse times 0, which I know is 0. A inverse times A, we know, is the identity, right? By the definition of the inverse. So I have identity times C is equal to 0. What does that imply? This implies C equal to 0. But what do we know? C is not equal to 0. What do we have? Contradiction. Right? So we assumed that the unicorn existed and did a series of logical steps that must be true if the unicorn exists, and arrived at a contradiction, right? We said assume A inverse exists. Okay, logical step, logical step, logical step. Now we have a contradiction. So that's basically the style of the argument. Are there any questions on how we arrived at this or how we got here? Okay. Oh, question, yes. The question was, if the columns are linearly dependent, will Gaussian elimination always result in infinite solutions or no solutions? The answer is yes. We proved that, basically we proved that if the columns are linearly dependent, then Gaussian elimination cannot give you a unique solution. Not a unique solution means either there's no solution at all, or there's many. Just for vectors, because in a matrix you don't necessarily have a unique solution situation. But we can talk about that more. I'll take questions offline. Feel free to come up to the front of the class. I'll stay here for 5 more minutes. See you next week, or see you Thursday.